I should give an introduction.
Yes, sir.
Yeah. Who are this one? I can't hear them also.
No, sir.
Okay.
Only chart.
Okay. Cool. Okay. Welcome to this session on fundamentals of transport processes. I'm happy to take all of your questions. As I said in the introduction lecture, what we will be looking at is um, how do processes affect the transport of material, energy, and momentum at the fundamental scale in such a way that we get at the large scale all of the phenomena that we are observing, and based upon that, what can we do to design systems, equipment, etc., in order to um, uh, achieve a specified outcome from these processes. Okay, so let me take some questions here first. What is the difference between dispersion and diffusion? Okay, this is a very important question. Uh, what is the difference between dispersion and diffusion, and why is dispersion not considered a molecular phenomenon? Okay, so let me try to explain it by okay. Let's say you have a container, okay, with some water in it, okay, and if that water is completely stationary, and if you put a spot of dye somewhere, okay, it's going to diffuse, okay, and then it will spread out, and then the concentration will decrease with time. Okay, if you did the same experiment, but rather you heated it from below, okay, right, then you will the water that is below will have a higher temperature, and the water above will have a lower temperature. Okay, so if I plot, okay, the temperature as a function of height, the water below will have a lower temperature, and the water above will, I'm sorry, the water below will have a higher temperature, and the water above will have a lower temperature. And because of that, the water below is lighter, okay, and lighter fluid tends to rise because of buoyancy. And because of that, you will have convection currents that are set up, okay, due to this heating from below. You will have water, cold water from the bottom rising up, going to the top, and warm water from the top. Sorry, yeah. You will have warm water from the bottom that rises to the top, okay, and cold water from the top will come to the bottom, okay. And similarly, in this case, warm water rises up and cold water comes down. And because of that, that carries along that spot of dye with it, okay. And because of that, it will mix faster than it would under just simply molecular diffusion. Okay? So this is transferred due to the fluid motion rather than the molecular motion. It is transferred due to the fluid average velocity. Okay, and as you increase the temperature, you will see that these convection rolls become more intense, and they will also become smaller. Okay, you'll have smaller rolls which become more intense. Okay, so that if you look at one particular position and you plot the velocity, let's say the velocity in the vertical direction as a function of time, you will get fluctuations in this velocity. Okay, these are fluctuations in the fluid velocity. Okay, not in the molecular velocity, because these fluctuations are taking place at a scale which is much larger than the molecular scale. Note that the molecular diameter is of the order of about a few angstroms. Okay, so because of that, the molecular velocity fluctuations, as I said, in a liquid, the length scale for the molecular velocity fluctuations is of the order of a molecular diameter, which is a few angstroms, 10 power minus 10 meters. In gases, it is comparable to what is called the mean free path, okay, which is zero point 0.1 microns. whereas this motion is taking place over a distance comparable to centimeters. Okay? And because of that, this is referred to as a fluid velocity fluctuation rather than a molecular velocity fluctuation. Similarly, in the atmosphere, for example, we have winds blowing. If there were some smoke that were discharged into the atmosphere, and if everything was perfectly stationary, absolutely no flow, okay, the smoke would still would still spread out, and it spreads out because of molecular diffusion. Okay? But the moment you have winds, right, they will carry this along, and these winds are um, they are turbulent flows in the sense that they have eddies of many different sizes, all the way from meters or kilometers down to centimeters or millimeters. Okay? So the smallest eddy in a turbulent flow, for example, will be of the order of 1 to 0.1 millimeters in size. But these are still fluid fluctuations because the size, which is 0.1 millimeters, is still much larger than the size of a molecular motion, which is 0.1 microns. Okay? So these are fluid velocity fluctuations. And these fluid velocity fluctuations, when they carry material with them, that leads to what is called as dispersion. Okay? Okay? Whereas if it is carried by molecular velocity fluctuations, it's called as diffusion. And you can estimate what is the magnitude of the dispersion and diffusion coefficients if you just know what is the characteristic length and the characteristic velocity. Okay? The diffusion coefficient, if you recall, okay, has dimensions of length square time inverse. Okay? So it is a characteristic length scale, okay, times the characteristic velocity. Okay? The characteristic length scale is the mean free path in molecular diffusion for gases, and the molecular diameter in molecular diffusion for liquids. The velocity is the molecular fluctuating velocity. And for diffusion, both of these can be calculated quite easily. The mean free path, as I told you, in the lecture we discussed that this goes as 1 by root 2 pi n d square, where d here is the molecular diameter, okay, and n is the molecular number density. Okay, so it goes as 1 by root 2 pi n d square, and this fluctuating velocity goes as the thermal velocity, so it's going to be the root mean square root of kBt by m. Okay, and we had estimated both of these in class. Okay, this worked out to be about 300 to 1000 meters per second. This worked out to be about 0.1 microns, okay, which is about 10 power minus 7 meters. Okay, and on this basis, for gases, if you multiply these two, okay, the mean free path times the molecular size, you get something that is roughly 10 power minus 5 meters square per second as a typical diffusivity in a gas. Okay. A diffusion coefficient in a liquid is smaller still because it will go as the molecular diameter times the velocity. Okay. The molecular diameter is 10 power minus 10, whereas the velocity is the same. It's about 300 to 1000 meters per second. 10 power minus 10 meters is the molecular diameter. 1 nanometer to 1 angstrom. Okay. On this basis, you get about, as I said, 10 power minus 8 meters square per second. Okay, as the estimate for the diffusivity in liquids. But this is an overestimate because, as I discussed in the lecture, in the case of liquids, the motion of one molecule in any one direction requires the cooperative motion of all other molecules that are surrounding it. Okay? In liquids, the molecules are densely packed, so the distance between molecules is comparable to the molecular diameter. So if one molecule has to move in any one direction, then there has to be a cooperative motion of all the other molecules around it, okay, so that this molecule can move. So the actual estimate is 10 power minus 9 meters per second, meters square per second for the diffusion coefficient in a liquid. Okay, so those are the estimates for diffusion coefficient. Why do I say that these are molecular properties? Because in calculating these properties, I use the molecular length scale and the molecular velocity. This is not the fluid velocity. The fluid velocity is much smaller. Okay? In most flows, our fluid velocities will be 1 meter a second or less. Okay, so uh, since I've used molecular velocity and molecular length here, this is a molecular property, the diffusion coefficient. It depends on the molecular diameter, the molecular velocity, which depends upon the temperature, the mass, and so on, molecular mass, and so on. Okay, so in that sense, this is a molecular property. It depends only on the molecule that is comprising the liquid. Okay. On the other hand, dispersion, okay, that depends upon the velocity with which this fluid is circulating, for example. Okay, or in the atmosphere, it will be depend upon the velocity of the wind. Okay, it does not depend upon the molecular properties, the speed with which the molecules are running around and colliding with each other. It depends upon the large scale motion of the flow. Okay, and depending upon the length scales of the large scale motion, we can get these dispersion coefficients. And these dispersion coefficients are not the same for the same material. It depends on the flow. The dispersion coefficient, for example, in a cyclone, for example, will be much larger than the dispersion coefficient in this room where I switch the fan on. Okay, and that is because it depends on the molecular properties. Whereas the diffusion coefficient in both cases will be the same, right? Because it depends only on the molecular properties, not on the flow properties. Okay? So the dispersion depends upon the flow properties. So if I have a flow with characteristic length scale of 1 centimeter, say, okay, as in this case, and I have velocities of, let's say, 1 meter per second, okay, my dispersion coefficient is going to be equal to 0.01 meters into 1 meter per second. Okay, which will be equal to 10 power minus 2 meters square per second. Okay. So you can easily see that this dispersion coefficient is actually much, much larger than the diffusion coefficient here. Okay. And that is because even though the length scale, molecular length scale is much smaller, the molecular velocities are much larger, but the product of those two, okay, for dispersion, for the large scale fluid motion, is larger than what it is for the diffusion coefficient. Okay. So that is an explanation of why dispersion and diffusion are different, and why dispersion is not considered a molecular phenomenon, because what is driving dispersion is the flow. Okay. It depends upon whether this room is cooled by a small fan or a large fan, the rate at which fluid is circulating. Okay. Even though the air is the same, okay, the molecular properties of the air are the same. Okay. If you drive it faster with a larger fan at higher speeds and generate more fluctuations, then the dispersion coefficient will change. Okay. So that's the reason the dispersion coefficient depends upon the flow. Okay. It's not just a molecular property. What boundary conditions are needed to solve fundamental equations? Okay. So we will see a little later when we come to that, but all fundamental equations whether it is the mass, momentum, or energy equations, they will turn out to be what are called second order differential equations. In space and first order in time. Okay. There are second order differential equations in space and first order differential equations in time. Okay. An example that you might have already seen or you will see shortly is the concentration equation. The time derivative of the concentration with the rate of the partial derivative of the concentration with respect to time is equal to a diffusion coefficient times d squared c by dx squared. Okay. So therefore, there are two kinds of conditions that you need. One is what is called a boundary condition, right, that applies to the spatial derivatives, and the other is what is called an initial condition that applies to the time derivative. Okay? So that if you know what the conditions of the boundaries are, and if you know what the initial state is, then you know what the state is at later times by solving this differential equation. Note that there is a second derivative with respect to position. Okay? That means you require at least two conditions on the boundaries, okay, the conditions on two boundaries in order to solve it. Okay, so if you recall, if you solve a second order ordinary differential equation, you end up with two constants of integration, and therefore you need two conditions in order to completely specify the constants in the equation. So second order in space, you need two conditions. The conditions could be either that the concentration is fixed on two boundaries in the x direction. Okay, C is equal to C naught and C is equal to C1. Say. Okay, the concentration is fixed at two boundaries, or you could have the flux being fixed. Okay, if you had a no penetration condition, then the flux at one boundary would be 0 and the concentration would be fixed on the other boundary. Or alternatively, you could have zero flux conditions on both surfaces. Or alternatively, you could have constant flux conditions, that is, the amount of material coming in per unit time is a constant on that boundary. Okay? So those are the kinds of conditions that you can have. You need at least two, okay? One on each boundary. Okay? If you had a three-dimensional system, then this equation will contain three spatial coordinates, x, y, and z. And the equation is a second order differential equation in each of the three coordinates, x, y, and z. Okay? And therefore, you will need two boundary conditions in each of those coordinates. Okay? We will solve equations of this kind when we do unidirectional flows. Okay? So, for mass transfer, you need either the concentration to be specified on the boundaries or the flux to be specified on the boundaries. In heat transfer, once again, you need either the temperature to be specified on the boundaries or the heat flux to be specified on the boundaries. For momentum transfer, the variable is the velocity or the momentum density. So you require either the velocity to be specified on the boundaries or you require the momentum flux, that is the shear stress, to be specified on the boundaries. Okay. So those are the fundamental equations that you require to solve. For example, for the mass, heat, and momentum transfer in a CSTR. So in a CSTR, you would have an inlet condition. Okay, at the boundaries, for example, on the walls of the CSTR, right? For the mass, you'd expect that there's no penetration through the walls, and therefore zero flux conditions will be applied for mass, except at the outlet, where whatever fluid is there in the CSTR is removed at the outlet. For heat, depending upon whether the CSTR wall is heated or not, you either apply a constant temperature boundary condition if the wall is maintained at a constant temperature, or if you're doing electrical heating where you're giving it some pre-specified flux of energy, then you specify the flux of energy at the walls. And for momentum transfer, the velocity has to be 0 because of the no-slip condition at the walls. So typically the velocity at the wall for a solid surface will be 0 because the fluid velocity and the solid velocity have to be equal at the wall. So you'd have a no-slip condition, which means that at the walls the velocity is equal to 0. And if you have some impeller or something that is rotating the fluid, then on the surface of the impeller, the velocity of the fluid is equal to the velocity of the impeller itself. Okay, so that will be the boundary condition for the momentum exerted on the flow. And finally, if a PFR with a very high recycle ratio is considered, how does it affect the boundary conditions used? The recycle ratio does not affect the boundary conditions because the boundary conditions are determined only by the interaction of the fluid with the boundaries. Okay? So, regardless of the recycle ratio, at the walls of a PFR, if I take that as some kind of a pipe or something, the boundary condition at the wall for the mass will be that there should be no flux across, because the boundary is an impenetrable medium, so there should be no flux going across the surface. Okay? The temperature condition would be either a constant temperature, if that PFR is maintained at a constant temperature, or it could be a constant flux conditions if you're giving a constant input of energy at the wall of the PFR. Okay? And the momentum condition is, of course, the no-slip condition, that the velocity at the wall of the pipe is 0. Okay? So, for example, if I have a PFR here, okay, you know that we plot the velocity profile as some kind of a laminar velocity profile. the velocity at the wall itself is set equal to 0. Okay? That is because the pipe is not moving, so the fluid at that surface has to be equal to 0. Okay? And then it increases towards the center because there's a pressure force that is driving the flow. Okay? And for a laminar flow, you'll get a parabolic velocity profile. For a turbulent flow, you'll get something that looks more plug-like. Okay? But in both cases, the velocity has to decrease to 0 at the wall of the pipe. Okay? That is a necessary condition. Yeah. Does turbulence increase mass transfer rate? Yes. And that goes back to the same distinction between diffusion and dispersion. Okay? If I have a laminar flow, right, I have nice, smooth, straight velocity streamlines everywhere. Okay? And recall that convection affects the transports mass, momentum, or energy only along the flow direction. In this particular case, there's no fluid velocity perpendicular to the flow direction. Okay? The fluid velocity is unidirectional. It's only in the direction of flow. Okay? And therefore, mass transfer perpendicular to the direction of flow, okay, mass transfer or heat transfer perpendicular to the direction of flow, has to take place due to molecular diffusion. Okay? And I had estimated the diffusion coefficient for you earlier. This is 10 power minus 5 meters square per second for gases, and it will be about 10 power minus 9 meters square per second for liquids. Okay. On the other hand, if the flow becomes turbulent, okay, of course, the mean velocity, okay, looks more like a plug-like profile with a smaller curvature at the center and sharper gradients at the walls. Okay. But over and above this, over this mean flow, you also have fluid velocity fluctuations in the form of eddies. Okay. And these eddies can transport mass or energy across the flow. Okay. Because the fluid velocity fluctuations are in all three directions. Okay. They are not only in the flow direction. And so because of that, these could transfer energy across or mass or even momentum across the flow direction, okay, because these are parcels of fluid that are traveling across the flow, okay, and that could result in a much faster transfer of mass, momentum, and energy. Just to give you an estimate, if I take the length scale of these eddies as 1 centimeter and the velocity, okay, of these eddies as, let's say, 10 centimeters per second for a typical mean flow, then the diffusion coefficient is equal to L times V, which if I write it down in terms of meters per second, meters square per second, this will turn out to be 10 power minus 3 meters square per second. Okay? And because of that, this, as you can see, this dispersion coefficient due to a turbulent flow is actually much larger than the diffusion coefficients you can have here, especially in liquids. Okay, in liquids, the diffusion coefficient is actually very, very small, and it will be nearly impossible to have mixing in liquids over reasonable time scales unless you have dispersion. Okay, so when you cook food and you heat water and the water starts boiling, it is the circulation of the water that actually transfers the energy. Without that, it's impossible. The time scales for diffusion in liquids is very, very slow, as you can see over here. 10 power 9 meters square per second is meters, right? The time scale, diffusion time scale in liquids will scale as length square by d. Okay. Note that diffusion coefficient has dimensions of length square by time. So in order to calculate the characteristic diffusion time, I have to take length square divided by the diffusion coefficient. And you can see this is equal to 10 power minus 4 by 10 power minus 9. This is 10 power minus 5 and 10 power plus 5. Ten power 5 seconds. 10 power 5 seconds is probably of the order of a week or so. Okay, so if you just wanted molecular diffusion to mix or to transfer heat or to transfer some mass, a spot of dye, for example, across this, you have to wait for a weeks. Okay? But fortunately, we have dispersion, which tends to transfer in much faster in much shorter time scales. So, yeah. So, is there any questions? Yeah, I don't see any questions with the live stream. Yeah, okay. If there are no further questions, I think we can end the session here. And kindly let me know if you have any further questions. We can conduct this session anytime you want. Just give me some notice and I'll come and answer your questions once again. Okay, thank you. So I'll see you in the next live session.